Welcome everyone to our uh, next TDS webinar. And today it's my great pleasure to introduce Professor Stefania Santini. Um, so she has been working on time delay systems for quite a while. And actually, I believe I met her at one of the TDSs many years back the first time. But at
Yeah.
the same time, she also works on applications which I think are very interesting. In particular, today she's going to talk about multi-agent systems. And then, of course, that's a very broad area itself, and there are many uh, applications where this comes up. So we are very much honored to have Stefania today. And Stefania, the floor is yours.
Thank you very much for this very, very, very kind introduction. Uh, you know, I'm Stefania, as Gabor said, and we're going to talk on multi-agent system in the presence of delays. The area is very broad, as Gabor already mentioned, so my idea is to show how this mathematical framework can be really used in order to solve engineering application, real-life problems. So to see how this mathematical framework is very suitable in order to really give a contribution with respect to real life solution of problems. Okay. So in that perspective, let me say that this is the agenda. We are going to talk a little bit about multi-agent system and the presence of delay. And we're going to connect this mathematical framework mainly to the idea of solve control problem in an area that is called cyber physical systems. So all these systems in which there is a communication that allows an interaction between the different physics objects. And in that way, the idea is to leverage the information that is spread through communication to allow some interaction and to make a kind of global behavior arise in the network. The importance of delay distributed controller is the thing that I hope that comes out from my talk today, in the sense that the time delay system theory is not just a way to represent the system, an elegant framework from the mathematical viewpoint, but to me is a very powerful tool for real world application. And I hope that the talk will be inspiring to try to apply this theory in different kind of aspect of reality. In that respect, the talk will focus on two exemplar application. One is related to the area of intelligent transportation system, which is an area in which I work a lot from a lot of years, starting from the automotive, then landing on the more modern intelligent transportation system framework. And on the other side, cyber physical energy system, we are going to talk to this and we're going to focus on microgrids. If there is time, we talk about further applications, some ongoing work. Since we are talking about application as well, the talk will be not only related to the description of the mathematical derivation of the algorithm, but will be also dedicated to understand how to validate once you design an algorithm within the framework of time delay system, how you have to validate it in order to be sure that it's suitable for facing and solving the challenges that arise in real world application. And so in doing so, I will show some experimental facility, experimental results that describe our lab that I just from the very beginning of the talk I'm going to thank because of their great contribution to this presentation. So what's multi-agent system, at least in the way that I want to leverage during this presentation, we can imagine it as a set of n-dynamic agents that are capable of interacting via a communication network. So what's going on? You have an agent over there, which is a dynamical system. It is autonomous in the sense that it has the capability of taking its own decision, okay, at agent level, so device level, but in doing so, it can for sure exploit information that are coming from the neighbors within its communication radius, okay. Um, the idea is so already here in the sense that we are looking to fully decentralized approach, okay, the localized approach in which we don't have a central orchestrator, okay, that impose a dynamic behaviors of the system, and we want that this dynamic behavior, common dynamic behavior, arise from the interaction of all the agents, although the decisions are taken at the local level. In this perspective, the agent is a dynamical system, so it can be mathematically represented, at least in a control-oriented way, from a model, a mathematical model, and the model can be linear, nonlinear. The degree of complexity of the model is really related to the application, and for sure, we induce some simplification in describing the dynamics, and we are then during the validation phase, we have to be sure that the assumption that we made fit with realities and that the behavior of the system is correctly induced by the control, even in presence of uncertainties or external disturbances that are related to the environment. Okay, if the agents are equal in dynamics, we think that the mass is homogeneous. If not, it is heterogeneous. Okay. Since we are looking to coordination of different agents that are going to share information through a communication network, the other actor on the field is the communication topology that can be mathematically represented by a graph. So graph theory is another element we have to take into account when we are designing control of such a system, in which some very well-known elements arise, like for example the adjacency matrix, that provide us information about which is the link, which are the connection, who is connected with who, and most important, we have also to account of the information flow. So graph can be undirected or directed, and this strongly depends on the kind of communication and from the technology aspects of the communication itself. So, if we say so, it's clear that we are going to look to mass approach for solving control problems that are related to cooperative collaboration among systems of devices. That can also be seen kind of Internet of Things in a certain way, but it's more than that. Because all these physical elements which are connected by the communication network in the ensemble turn out to be a cyber-physical system. A cyber-physical system is just that, is a system in which the different physical devices are connected and exchange information through the communication network, and the overall behavior cannot be understood if we do not think to the very strong interaction between the physical reality and the digital reality on the top, that is related to sensor, actuators, hardware capability for computation, and of course, communication capabilities. So the idea, once you interact and you cooperate, you can, as already mentioned, have a common behavior at network level in order to, for example, reach a desired common global behavior called common global goal. And the goal that you want to achieve in this cooperative framework strongly depends on the specific problem. So different kind of problem may arise and can be stated, for example, consensus, in which there is a common emerging behavior, natural common emerging behavior toward a certain constant states or values, or synchronization and leader tracking, if we think that all the agent must follow a predetermined behavior which is set from one of the actors inside the network that is called the leader. That can be one of the elements of the network, can be also a virtual leader in a certain way. Then we can also use this framework for formation control, containment control, or bipartite control if we think the agent not only as collaborative but also as antagonist in some specific kind of application. Since my goal is to use the framework to solve real life problems, let me say that the cyber-physical system from the applicative way is a paradigm that matches a lot of reality. We can represent as a cyber-physical system a smart city, We can represent as a cyber-physical system a vehicular network or a smart industry problem, thinking about Industry 4.0 or 5.0. We can also think something like e-health. So every time that we, or as I already mentioned, energy grids, microgrids. So there are many applications that can be seen as a cyber-physical system. And so the level of abstraction is very important because by this way, this framework, you can use the same kind of tools in order to control different kind of reality. Um, since the idea is to cooperate in this kind of physical paradigm, the communication is the key. And we have different kind of communication protocols. And these are really related to the application that we are looking to. In the sense that if you look into transportation, we have some communication standard that, for example, allow vehicles to be connected among each other and with the infrastructure along the so-called V2X paradigm, in which you can have a protocol, a Wi-Fi protocol, like the IEEE 802.11p and its evolution, or you can have 5G and now the emerging 6G networks. You can have communication standard for the smart grids or for the smart manufacturing that are short range, Wi-Fi, and so on and so on. However, whatever is your communication network, you have always an aspect in common that are some latencies. It is impossible to operate a communication network without accounting these latencies. And these latencies emerge, are present every time, also during normal operating condition of the network, although are bounded and they can be estimated, this upper bound, and different upper bounds may arise depending on the kind of technology that you use for communicate and the kind of protocol. Of course, the communication scientists are trying to lower these latencies in order to improving network infrastructure, reducing the processing time of the data, optimizing the transmission protocol, of course, or optimizing the propagation delay due to quaking or buffering of the signal. But however, some latencies always arise, and from the control viewpoint, since these impairments, natural impairments related to communication that arise in normal operating condition, as already said, you have to think about it when you design control from the very beginning of the control design phase in order to provide a kind of robustness with respect to the delays, resilience with respect to delay, and also estimate in a very clear way the stability margin with respect to delay to be sure that this stability margin are within the upper bounds that are set by the technological framework. Another problem that arises that characterize practical application with respect to theory is the fact that when you consider physical dynamical system that are interacting over a communication network, the delays in the sharing of the information, okay, here represented as tau, strongly depend on the actual communication link. So you cannot think easily that you have a homogeneous delay all over the network, okay, or that you have a fixed constant delay, because what's going on that this time delay really depend on the condition, the actual current condition of the specific link. So delays in this kind of scenario must be seen as heterogeneous or multiple and for sure time varying. So the idea when you're using mass theory in the presence of delay, you have to think to time varying delay. This is the first issue that you have. Now, when the delay come to the ground, they come to the ground in control to the fact that you want to take decision at the local level, for example, at the agent level. You see this agent that is indicated by the red circle over there. But what's going on that this agent takes its control decision on the base of its local information as well as the information that are coming from the neighbors. So what's going on? That these information that are coming from the neighbors, so within its communication range, which depends on the communication infrastructure for sure, what's going on that this information comes outdated, delayed. And so the control protocol that is computing on the base of this information is a delayed one. And this means that at network level, the overall closed loop system is a delayed one. And so stability condition for the closed loop network should be driven or should be carried out considering the presence of delay and trying to tune the control gain so to assure some suitable delay margin for stability. Okay, so the numbers of delay that may arise depends for sure from the number of actors, and so you can have a complexity in dealing with the system depending on the number of agents that you are considering from one side, and also depends from the kind of graph that you have, so the topology of the network. Not always the topology is a one is a all-to-all, so everyone is connected with everyone. But mostly in the application, since there are some communication ranges, what's going on that we have a kind of graph that depends on the distances, okay? Um, when thinking about this specific thing, this increases for sure the complexity of the system. The only hypothesis that we have to do from the theoretical point when related to the graph is the fact that there is a direct spanning tree rooted at the leader if you want to solve some leader tracking control problem of the mass of the delayed mass. But usually this is an assumption that is accomplished normally during the application, because what's going on when you construct an application, the leader somehow has to spread the reference signal through the network along a given path. Most of the results in the literature consider so heterogeneous time varying delay under the assumption that delay is bounded, which is a reasonable assumption because the delays of communication network in practice are bounded, although they can be large. Once we have set our theoretical framework, let's move to the central part of the talk, that will be how we can use or leverage this kind of framework, okay, in the proper way in order to solve problems. And to do so, we introduce two main illustrative examples. First of all, intelligent transportation system framework. In doing so, I will refer to what in mobility is a new paradigm that is called cooperative connected automated mobility, CCIM, that has been indicated from the European community as a game changer in shaping the future of mobility. In this kind of paradigm, the road itself is smart or is digital in the sense that every vehicle on the road can communicate with the other vehicles within the communication range, but they can also communicate with the infrastructure as well in order to have information about what's going on behind the line of sight. So the idea is to use communication to make every vehicle, every actor along the road aware of every possible dangerous or non dangerous situation that is behind the line of sight. So actually, the vehicle can use perception and sensing in order to sense what is around, but through communication, they fulfill to see farther. And leveraging the infrastructure, this line of sight is even more extended. And what's going on over there? Since I know something that is happened far from me, I can adapt my driving behavior in the proper way. For example, if I'm aware of future or traffic jam, I can reduce my velocity or I can impose, the information in order to have a sustainable motion to the car. For example, I can use information of the surrounding, of the traffic, or the adiabato in order to optimize fuel consumption. So optimize my kinematic motion in order to minimize for fuel consumption, or optimize the way that I operate my battery, increasing the autonomy of an electric vehicle, or I can make the traffic more fluid in the sense that if I know that there will be a stop in front of me, I can decrease my velocity and I can have a more fluid situation, avoiding some tip in, tip out behaviors that are the ones that are responsible for the loss of safety and they increase the emission. Okay, so for this reason, um, CCIM is a very important paradigm, okay, that will for sure shape the way that we see the road in the next future. Just to let you understand, this is not something on the future. The roads are just organized like that, and even if we don't have fully autonomous vehicle on the road, we can have automated vehicle as well, in which we have some ADAS system, so some driving functionality are supported by control algorithm that help the driver in some specific situation, for example in adapting the velocity if we think the cruise control. Moreover, most of the car are equipped with the possibility to understand their localization through GPS, so they can be aware of their position, velocity, acceleration. If, and it's common nowadays, and when you drive a car, you look to a map in order to understand where are you going and to route exactly to your destination. Within this wide um, transportation framework. In this talk, I will talk more carefully on platooning, or I will use platooning or platooning driving as a kind of exemplar application in transportation. What is a platoon is the possibility that the cars drive the longitudinal motion as a fleet and they move forward along the line in a coordinated fashion. Okay, there are many advantages in doing so. First of all, you induce a common velocity behavior, while you can have a very, very small intervehicle distance related to some formation geometry information. And by this way, you can have a traffic flow that is more fluid. You can optimize the driving behavior. You can minimizing the effect of the aerodynamics. And by this way, you have a more safe, a more sustainable way of moving along the road. In this kind of paradigms look simple because we are moving along a line, right? Along a straight line. But although it is so, from if we think to platoon as a cyber-physical system, this is not the case because there are different kind of topology that may arise depending on the communication structure. So depending which are the active communication links, which are the information that are exchanged. In this kind of paradigm, the control is fully decentralized in the sense that each car can take its own decision, so it can impose a desired acceleration and braking, okay, but in doing so, the overall behavior at the ensemble level will be a common one. So everyone will be moving with a constant velocity and reaching and maintaining a desired intervehicular distance. The common velocity can be set by a leader agent that, for example, will provide to the other an optimized kinematic profile to be tracked and followed, that can be optimized by the leader, that can be the first car in the platoon, or that can be even a virtual platoon if we think that the virtual leader is infrastructure. And by this way, he will command to all the others the right or the optimized kinematic behavior to be followed in order to achieve, for example, some sustainability goal, or to optimize the traffic jam, or to enhance the autonomy if we think a fully electric platoon and we think to electric mobility. Um, so if we describe the platoon problem, so the idea of reaching and maintaining a formation, it's clear that it's a cyber-physical system, and also clear that it can be very easily represented with a multi-agent system architecture in which the agents are the vehicle themselves, and they can take motion decision, the driving decision, by also using the information coming through the network from the other vehicles within their communication range. If it's so, the idea is to recast the plateau formulation as a leader tracking or a consensus problem that should work with different kind of topology. The different kind of topology may arrive, and to be sure that whatever is the topology, you can obtain your goal. Here there are, for example, the most common vehicular topology: predecessor follower, leader predecessor follower, bidirectional, all to all, and so on and so on. Before moving to the theory and to see how to address this kind of problems, let me say that once you have deployed your contour algorithm, leveraging mathematical paradigm of time delay system, look into the multi-agent framework, delayed multi-agent framework, it's always important to see if then in reality everything works. So if you're interested in working with applications, so control application, never forget to use some specific tool that helps you to test your solution in the proper way, starting from the classical model-based control design in silico, moving with Hill hardware in the loop experimental validation, in which you have to consider different kind of very detailed models of the cars on the road. You have to take into account the traffic. You have to take into account a real-time control algorithm that should be implemented with some specific real-time hardware. For example, here there are the space and Scalexio, or you can use a virtual environment experimental validation tools in which you can have a small vehicle on scale that move in a virtual reality. So they move along the map, imagining some traffic flow, imagining some city, some structures, some road, some signaling on the road, and so you can see the effect of the environment on the algorithm that you are facing. And finally, some experiments directly on the road, on the car, obviously. These are some of the facility that I have in my lab, Daisy Lab. So if any of you would like to join me in this kind of research, we will be happy to share our facility for research with you. So let's go back to theory. And the idea is to solve the platooning problem, and the idea is to recast it as a consensus problem in a multi-agent system framework in the presence of heterogeneous delay, which are time varying. These results are related to some first attempt that goes back to 2014, and in which we solved the problem. We solved the problem as a second order consensus problem. So to reach the formation geometry and the common constant velocity within the platoon, the intervehicular distance, the ij, depends on some spacing policy that can rely on some headway time that gives you the idea the how safe, how close safely you can be when you're driving or you're operating your car as a platoon. And this for sure shapes depends on the velocity in which you're running, for sure, plus a certain fixed distance, which is the distance that the plateau formation should achieve at a standstill. If you do so, as already mentioned, you have to work with outdated information, so your protocol is a delayed one. We see over there a diffusive protocol, essentially, in which AJ takes into account the specific topology, so the presence of absence of a link among the edges, okay? When you put your control input and you derive your closed loop network, you end up with a network dynamics that is a vehicular network dynamics that is a time delay system. And so to achieve the stability over there, you have for sure use time delay instruments or the tools that are related to the delay system framework. Let me say, before introducing the result, that for sure there could be other way of solving the platooning problem. Now it's very popular to go with, for example, with the eye. But why is very important is said to use a very consolidated, elegant mathematical framework, because this framework provides you guarantees about the stability of the solution of the vehicular network, but not only allows the proper tuning of the control gain, so that you can also provide in an explicit way the estimation of some delays stability margins. And this is very important because this gives you an idea of the ability of the solution of working with an actual real communication network. For this specific case, we have analytically derived the stability margin and the tuning of the control gain by performing a closed loop proof with the Lyapunov-Razumikin approach. This is not the only thing that you have to do. Once you have proved from the analytical viewpoint the capability of the fleets of reaching and maintaining a desired behavior, you have sometimes to prove another very important results that is indicated in two, which is the string stability. String stability is a kind of special stability in the sense that it's not really the capability of reaching from different initial condition your formation, but what's going on instead of the equilibria. So if you have a perturbation on the head of your formation that moves along a string, the idea is to de-amplify this oscillation to the tail. This is very important because the leader can have some tip in, tip out during the motion, so it's very important that this kind of disturbances will be de-amplified during along the platoon from the head to the tail. And this is usually done by leveraging some sensitivity function in the Laplace mathematical framework. And for this reason, you have to look to a constant delay. And usually you do this analysis at the worst case, imagining having an idea that your delay is constant, it is equal to the maximum. So you think to a worst case scenario, approximate the delay with Padé, and you do some analysis with the sensitivity in order to test if for your upper bound you have this very nice behavior that is related to the capability of de-amplified the perturbation, and to be sure that this perturbation do not affect the spacing of the vehicle, okay, the formation geometry. So once you have done this, you have to test it. And as I already told you, the testing is very tricky because you have used a very simplified model of the vehicle or even of the longitudinal dynamics. You can also leverage a linear one, but for sure you have neglected most of the nonlinear dynamics and the uncertainties. They are in reality, but then during the test you have to put them again on the ground. So part of the activity of people that is focusing cyber-physical system, not only in this application, but whatever application cyber-physical system, is to construct specific co-simulation platform that helps essentially to model the three main ingredients of cyber-physical system. First of all, the dynamics of the agents that must be more realistic and more close to your applicative domain. Then you have to model the environment, and then you have to model the communication network. That's why part of the work that we did, we helped the Plexe community. Plexe is a co-simulator that allows to model the road and the traffic through the facility of a traffic simulator, which is well known in the transportation community, which is Sumo. In this Plex, we had provided a very detailed model of the cars in order to consider different kind of cars, different segments, and different powertrain as well. But most notably, you have to consider the communication channel that here in Plex has been emulated or simulated, let me say, through the network simulator, which is Bains. We have also worked with other network simulator, for example, with Omnet++. And the idea is to understand that if I really emulate my communication network, if my stability margin with respect over their alpha field, and if I can for sure ensure that my solution is resilient and robust with respect to the communication impairments. The same kind of time delay multi-agent system can be used also to look to something very specific that is related to cooperative maneuver. When you're working with platoons, a platoon like this, it can be that a new vehicle won't join the platoon. And this can happen in a very simple way. For example, join at the tail. So I follow, and when I reach at the proper distance, then a communication link is activated. And I can also, even if this is the case, if this is the communication range, receive directly from the leader the information, but I can also have more complex maneuver, like for example, joining into the middle. So it can happen that my vehicle want to join in the middle of the platoon. If this is the case, what's have to be realized is that a gap should be open. So a distance must be created, some links should be break, the new vehicle must be inserted into the platoon, new communication links must be activated, and then I can run in the platoon. If we want to use the multi-agent time delayed framework to solve this kind of cooperative maneuvering, um, then you can use a delayed protocol. Here again, we have a different one for platoon in which you consider a switch signal. So you can organize your closed loop system as a switch time delay system in which you have the ability to switch among the different kind of topology given a certain dual time in order to perform your maneuver. If we think about this, you can try to solve the problem, for example, first of all, finding some lower bounds of the asymptotic consensus region, given the entire set of admissible switching topologies that may arise during the coordination and the maneuver, such that two consecutive switching systems are separated by some finite dual time. And then you can prove the stability of your switched closed loop network, for example, by using now a common Lyapunov-Razumikin method, common because you are in the presence of a switched system. This allows to tune your control within the region that you have defined at step 0, and then you can derive some stability condition that can be expressed as an LMI based solution in which that can be used to tune again your control gain in order to be resilient with respect to the presence of the delay, and also provide some delay upper bound. Here just an example of the join in the middle maneuver that you see over there, the one that I have introduced to you a few minutes ago, and here you see the changing of the adjacency matrices that undergo this kind of maneuver, and that you should be account for in order to perform this kind of maneuver as well. You can for sure test all these kind of thing by using, for example, the Plex simulator that I showed so far. It is very important indeed that you have an emulation of the communication structure, which is very precise in order to be sure that your theoretical results again match what's going on in practice. This kind of algorithm has been tested for sure along the road. For example, we did some testing. These are results that go back 2016. in Sweden, for example, as you see, we did this in an industrial area in Gothenburg, Sweden, in collaboration with Volvo. We did some experiments in which we not only have the design and tuned the delay controller, but we have also implemented them in the hardware into the car, and we also have taken care the communication box that is on the car and also the localization mechanism, because in order to spread your kinematic behavior, you have to measure on board, so you have to rely in a very proper way on GPS measurements or IMU, Inertial Measurement Units, in order to have an idea of your kinematic behavior and to transmit, to communicate, to share this information with the other actors in the platoon. The previous part was related more to consensus, so the idea that we reach and maintain a common behavior and the overall fleets march with a constant velocity, which is imposed by the leader or can be imposed or can be set equal to the legal requirements. So every segment of the road has a maximum velocity that you have to undergo, for example, but in other cases you may look to leader synchronization. So what's going on that your leader is changing is his velocity, is accelerating, decelerating, and this kinematic motion can be optimized or can be induced from the traffic jam ahead. So he has an idea what's going on ahead, and by this way his dynamic behavior changes. And every time his dynamic behavior changes, it must be properly imposed to the other followers into the string, into the platoon in the proper way. In this sense, you talk about leader tracking. And you have to solve this problem in the presence of time varying heterogeneous communication delays. We solve this as a third order. Here we also introduce the presence of the acceleration. Acceleration is a fundamental information in automotive field, and it also is very important that that the acceleration profile is carefully imposed by the leader to the follower in order to avoid variation in the jerk that can be uncomfortable for the passengers into the car. This problem has been solved through an adaptive distributed cooperative control law, in which the adaptation that you see, the heterogeneous gains are adapted through this adaptation law, and the idea is to use adaptation to provide some robustness with respect to external disturbances and uncertainties in this work. Here we see only the control protocol, and when you insert it into the dynamics of the system, you again end up into a delayed closed loop vehicular control network system, and you have to prove stability. Here with the Lyapunov-Krasovsky method, for example, the idea is always the same. Try to have some LMI-based criteria that can be solved, obviously, by using interior point and the normal solution for solve LMI system, in order to not only guarantee stability, but obtain a way to tune the gains in order to estimate the time delay stability margin and to be sure that your solution is compliant with the technology that you're looking to. And so every time you have to estimate the feasible maximum delay value, and you want it to be larger than the actual one that is in the nectar, in practice, okay, in order to be sure that you have a margin of stability with respect to this. These are again with blacks some results related to a trapezoidal maneuver. So what's going on that you cruise, you decelerate, you cruise again with a lower velocity. For example, the leader sees some traffic jam, so you have to move a little bit slower, and then you can increase your velocity again. You come back to cruising to the original velocity that you have to impose. And you see that with this kind of system you can really easily follow this despite the presence of delay. And you can also, every time however you look to this kind of thing, you not only have to sim some specific maneuver, but you have to consider also emerging maneuver. for example, as hard braking. What's so innovative is I have to brake very hard because something on the road happens and we have to stop, and you see that you have this very nice braking maneuver in which all the vehicle then stop at a standstill. In this kind of approach, is also important to test the system with respect to hard delays. So not only use the classical Omnet Plus or Vane's communication simulator, but for example, emulate the communication channel stochastically, for example, with the well-known Bernoulli and Gilbert channel, in which you have a kind of delay that goes from low delay or very hard delay in a stochastic way. Not only this is very important, what is very important when you do application also to check some additional KPI for the safety, for example. Here we have constructed a warning collision index, which is an index that says if there is the possible of, or if there is the possibility of an incoming collision, in order to be sure that during every maneuver you still have some safety. This is a very, very classical transportation index that has to account for the capability of braking of the vehicles. So you have to tailor with respect to the kind of segment of car that you're looking at, if you have heavy duty or normal car, and so on and so on. Another problem that may arise that can be solved is also to take care about parameter uncertainties. Not only leader tracking, but parameter uncertainties. There are a lot of parameter uncertainties in the vehicle, in the dynamic of the vehicle, but the most important one that you have to take care for is related to the powertrain. Not because you have just a nominal value for the powertrain constant that depends on the kind of car that you're looking at, the segment of the car that you're looking at, but really from the fact that the powertrain may vary this value depending on the actual driving conditions. So this kind of uncertainty must be carefully seen, and they have been considered by proposing a robust distributed cooperative PID control implemented in a fully distributed fashion, in which of course I consider the information for every action coming from the network. The network is always there in the coefficient of the Laplacian matrix that accounts from the link, the absence presence of the links. But what's going on here that we perform this analysis under the hypothesis that the uncertainty is bounded, which is not a crazy hypothesis in the sense that this kind of uncertainty are for their nature bounded. And so the hypothesis really fit what's in reality. When you consider inject your control protocol, you then derive your closed loop vehicular network. Here represented via the scriptal transformation, you end up with a delayed system that you have to consider and whose stability must be proven. And in this case, what is very interesting that you have to prove two things. You have to derive for sure LMI basic control gain tuning to provide both stability margin with respect delay and uncertainty. So the idea here is to construct a kind of stability region so that you know which are the gain that fulfill both your requirement with respect to the presence of the uncertainty and the presence of delay. Obviously, uncertainty bound should be taken equal to the one that in the automotive field are the one that are characteristic for example, the powertrain of a certain given vehicle. When you do so, such a thing, another important thing is to consider very complex vehicle dynamics. For example, we have also developed the lab platform that is called Mitras for the virtual testing, that with respect to Plex is more flexible in the sense that allows us to emulate onboard ranging sensor and V2X communication. In saying so, I want to stress something that maybe I have neglected or is under the line, that every time we perform an application like Platoon in our control protocol, we do not rely on sensors. Sensor may be introduced. We can have proximity sensors that are affected with the delay as well. But what is very important that we're looking to the capability to drive the car relying on the communication and the communication effects, because we want to consider a vehicular network at large, so we want to see how different vehicles reach and maintain a desired formation. And in doing so, you have to consider more complicated vehicles, dynamics that emulate realistic the powertrain, and that emulate in a realistic way the effect of the internal combustion engine or the electrical motor, if this is the case, and you can do by using some MATLAB approaching, while on the other side look to the traffic and the environment through the traffic simulator Sumo. Here we see some maneuvers. This kind of simulation are very important because allow you to do something to check really the resilience with respect to parameter uncertainty through very large campaign in which you use a Monte Carlo based approach, for example, based on the Latin hypercube sampling. So by this way you construct really great variation of the parameter in order really to check the resilience of what's going on when you move to more complex scenario in which the uncertainties are strongly present. Till this moment, we are talking about to use the mathematical framework of multi-agent system just for dealing with the latencies that are normal in the sense that are the latencies that are on when the network properly works. So even if the network is properly working, the communication is never ideal and we have inside some latency. However, these latencies may increase, for example, in the presence of a cyber attack. And this is very important. Every time you put a network on the top of a physical system, and this is true for every cyber physical system, then you can have some problems related to the fact that this communication network can be attacked by a malicious actor. Obviously, cybersecurity is a problem which is well known in the computer science, and computer science people defend the communication network in a proper way by external actors, extruder, that try to penetrate the network from outside. And in this case, there are many mechanisms that works very fine, encryption, decryption mechanism, or you can provide some blockchain a solution, for example, in order to increase the opacity of some information or preserve the privacy of some information. But what's going on that sometimes you don't have an extruder, but the attacker can be one that is inside the fleet. So you can have an intruder into the fleet that can try to do an attack on the platoon. And the control for sure cannot be able to reject this, but has to be resilient in the sense that we have to be sure that no crashes or no very unsafe behavior are induced in the vehicular network if there is this attack. So in the sense, you look the cyber security from the control viewpoint. Let the control to be resilient, to be prepared to this. The possible attack that you are considering on communication vehicle or network are two kind: spoofing, message falsification, denial of service, and two kinds: spoofing and message falsification. And this kind of attack are more or less related to the capability of the intruder of manipulate information or to inject some false information, or denial of service, buster mission, that are some attack on the channel that results at the end from the control perspective in very large delay. Again, you can use the multi-agent time delayed framework in order to counteract this. First of all, you can use the cooperation that is inside the framework of multi-agent system to construct a cooperative belief, and so to discard an information related to a malicious attacker, comparing every information to the belief, and so discard the information that seems to be compromised, and this uh, answer to spoofing and falsification kind of attack. And on the other side, you use the capability of the protocol to be robust with respect to great delays, large delays, through the fact that you have a control protocol, which is a delayed one that has been designed in order to counteract the delays. The conjunction of the two mechanisms allows you to reject or to preserve the safety of the platoon. For example, here we see a platoon of 4 cars, okay, undergoing a very strong spoofing. All the vehicle, there is an offset on the acceleration for all vehicles that is spread all over from the 70 seconds of the simulation, while the platoon is undergoing a very strong DOS attack, DOS attack from the very beginning of the maneuver. And you see that with a classical protocol, cooperative protocol, but without considering delay in the protocol, what's going on that you have that your position error increase, and then at the end you have a crash of idea that is represented by this star. If you look instead to the delayed protocol, you can see that even if you sense the presence of the attack, in the end you can safely, with a little bit of offset, recover your platoon information. These are different kind of result as well. They show how you can still perform a trapezoidal maneuver under a DOS attack, or and how the vehicle, after subjecting an attack that happens 130 seconds after a small transit, are able to recover the velocity and to track correctly the velocity of the leader. Virtual platooning can be also applied to crossing, in particular crossing in unsignalized sessions. So you see different cars that are coming from different routes. They start communicating in this circle, which is the communication zone. Then you have a conflicted zone, and you want that every vehicle pass the conflicting zone one at a time, so to be sure that there is no collision. Although the problem is complicated because it's a bidimensional one and you have a generic intersection, you can solve it by constructing a virtual platoon. So you consider a negotiation into the communication radio zone, and you negotiate, okay, and have the order of passing, and the order of passing is translating to the position in the virtual platoon. So you recast this problem in a longitudinal one. The order depends how far you are from the center of the conflicted zone at the beginning of the maneuver, and then you ensure to the virtual platoon that the distance is such that once pass here through the intersection one by one with a sufficient space and time, and moreover that the fleets crosses, okay, the intersection at the maximum common velocity, which is the one that is required by the law, so you don't have any stop and go phenomena and everything is very fluid. This kind of thing can be tested, and has been tested in Asta Zero with the collaboration with Ericsson during the development of their 5G, in which we perform this crossing with the delayed protocol that we based on the virtual platoon that I showed so far, and we consider the crossing of one truck and two Volvo car that were crossing the signalized intersection in a fully in a fully distributed way. And what is very important in this kind of experiment, we just focus on communication without relying on any sensing in order really to test the ability of the 5G network from Ericsson, and also the ability of our control protocol to deal with latencies also in this very safety critical application. I'm running out of time. I don't know why. It seems to me that I don't have too much time, but I want to skip for sure, go a little bit into my next topic, which is the cyber physical energy system. I hope I have time. This is another domain, completely another domain. But even if from the physical viewpoint you have a completely different domain, still the framework, the theoretical frame that you can use to deal with this is the same. And in particular, we can consider the so-called microgrids. In the microgrids, you have a different kind of energy sources that may be related to um, renewable energy. Okay. Everyone can be controlled by his local controller, quindi its local sensing, actuation, monitoring devices, but they are able to communicate using a communication network. The idea is to coordinate the energy flow in order to be sure uh, that everything is perfectly regulated. Also, because this kind of grid are used in islanded mode, or they can be attached again to the main grid, electric grid. So microgrid are spatially distributed intelligence system, and so they can be exchanging information through a communication network. They can be represented as a multi-agent system in which communication delay come to the ground. In particular, the control of this kind of grid is made up an architecture, a control architecture which is hierarchical. Usually you have that your energy resources are controlled by local controllers. Okay, this DG, that is the primary control, that is called group control. Then you have a third level which imposes some prescribed variable for voltages and frequencies according to some KPI that are optimized at the overall network level. And then you have this secondary control, that is the one that can be designed by delayed multi-agent system, in which you want to restore frequencies and voltage to the nominal values. So when there are some load changes, not only load changes, but also when there are some steady state errors that are due or are necessary to compensate error that are coming from the primary control. The group control can induce some fluctuation, and then you have this secondary control that is responsible to reset or restore the required voltage and the required frequency. If we look to this secondary control, this is really a problem of a cyber physical system, as already mentioned, and they can be solved using the same mathematical framework that we have used, for example, for Plato. The only main and very important difference that when you look into microgrids, the theoretical results that you're developing must be finite time. So you want to ensure that you recover your frequency and your load and your voltage despite the presence of perturbation in a finite time. Because the quality of energy is very important for the customer, so it's really something that should be prescribed. So you have to try to guarantee some prescribed transient performances together with the robustness, with disturbances and the presence of delay. We have solved this problem again through a distributed cooperative control protocol, as you see over there, and the overall grid stability has been proven through an LMI-based delay-dependent stability condition that allows to tune the control gain to assure some prescribed stability margin, and at the same time to be sure that the trajectory undergoes some dynamic performance threshold. As you see over there, this C2 is related to the required threshold. Again, when you look to an application, then you have to test really. And for example, you have to use in this field some test system. There are some standards for the testing of the algorithm. For example, we have validated it on the IEEE 14 bus tests. Here I show you some results related to this network, in which you have, this is the topology of the network. This kind of validation campaign for sure considers the undergoing Drup control effect on the network. So there is a physical based representation of the components during the simulation. And you see how you nicely can track the voltages and how you nicely can recover when there are changing of the loss. And most notably, you can see that while you can have a very smooth trajectory tracking or leader tracking when using our delay protocol, if you implement the same kind of networked protocol but without the delay compensation, then you can have a fluctuation, and this fluctuation are related to the presence, for example, of the variation or the small error induced by the plug and play by the Drup controller. Another issue that I just want to mention, I go very, very, very fast, and maybe if I'm running out of time, I will cut the last part of the talk, but we are really on end. Another thing that you want to prove when you look to energy grids and in which time delay mass theory is very important is related to the fact that you want to reduce the communication network workload. So you want to operate your network in the proper way. You don't want to burden the communication network too much, because in this kind of network it's very important to preserve the bandwidth with respect to activation. So you want to achieve, for example, secondary voltage control in a slanted way for energy supply, uh, and you want to do accounting for this optimization of the network load tool. If you do so, for example, an idea can be to use distributed cooperative dynamic event reader control. And these are the steps of the design. First of all, we have derived a distributed proportional integral controller in which the derivative action, which can be nicely be implemented by approximating the derivative action through a finite time difference approximation for the derivative term. Then you use a sample data implementation in order to make this control protocol digital and start to reduce the workload on the communication network, so ending up in a distributed PIR control. And third, for further optimize the operation over the communication network, you end up at step 3 by design a dynamic event trigger mechanism that use an auxiliary variable to reduce the inter-events time, and that in this case is based on the distance or on the error, let me say better, from the actual computed control input and the effective one sent to the actuator. Again, when you insert this kind of protocol, you end up with a delayed closed loop system, and then you have to derive some LMI stability condition that provides the exponential voltage restoration in the presence of limited communication resources, and you can derive the estimation of the sampling period as well that preserve the stability. You have to test this. There are some testing again on a test network. Here you see the SIM power system snapshot. What is SIM power system? Is a simulator that emulates from the physical point of view in the behavior of each component in real time, even the presence of inverter in the primary control loop, the so-called Drup controller. And you use this kind of model also together with some target hardware real time on which the controller run in order to understand with hardware in the loop experiment, in order to understand if this kind of a controller can be easily implemented in reality. And you see, most notably, that with the dynamic event trigger, you have a reduction of the control updates with respect to static ET and simple data, a simple data controller. And here, obviously, the performances that are in which you see how the required voltage profile is smoothly followed. Uh, Gabor, if I have enough time, if I'm not, if running out of time, I can skip the last part.
If you could skip, then maybe good, just because then we have more
Okay,
time for
what I want to do
questions.
is
Good.
that you can apply this kind of framework with other application, for example, platooning of train, the so-called retar coupling, or you can apply for formation control of robots, mobile ground robots, as you see over there. And what is very important to me, closing this brief talk, is not to provide tools, only mathematical tools, but show that this kind of mathematical framework that are related to time delay system can be really used as test to operate a real system. And so to encourage all the researcher to join us in trying to solve problem of cyber physical system by using the mathematical formulation of the time delay system. Again, I want to remark that there are other control framework that can be used, but what is very important of time delay system that you can really end up to guarantee some performances and you can really guarantee resilience with the delay, which is very important when you are touching some application which are, let me say, safety critical. Before going away, I want to take my lab, the Daisy Lab, all the guys that are here, all the guys that contribute to the research enhancement. I say thank you to them. I'm here just because they exist. Thank you, guys. And finally, I want to thank the TDS working group because they allows to host the TDS workshop, the workshop of time delay system of the IFAC community in 2027 in Naples. We wait for you all. We are honored, and I hope that you join us and you participate to this very nice event. With this, I think I'm finished my talk and I'm ready for question if there are any.
Thank you very much, Stefania, for this very nice and informative talk.